Hi, everybody, and welcome to today is actually, what is it? May 12th. We have quite a bit of material to cover. I know chapter 30 is getting a little bit long, and it's actually one of the longest chapters in this class. So we still have one item that we need to finish in this chapter, and then we're going to get some applications on the way. Done in this chapter. So let me get your notes. So basically we did the RL circuit, namely a resistor and an inductor. We did the LC circuit, and we found that that was oscillating, and its oscillation frequency actually turned out to be 1 over square root of LC, okay? And today, we're going to expand on that, and we're going to do the RLC. I was hoping that you have done the mass spring system with the viscosity in it. Since you didn't do that in physics 4A, or at least a lot of you don't remember having done that, so we're going to touch base a little bit with more in-depth RLC circuits. The math is identical. The math is similar, with the exception that instead of having a mass in physics 4A, now you have an inductance L. Instead of having a resistor in physics 4B, in the past you were dealing with the coefficient of viscosity, namely B. Instead of having a spring constant in physics 4A, excuse me, now you have the capacitance, which is 1 over C actually. And that's it. That is basically the analogy between them. And instead of how where you were targeting in physics 4A, the position basically, because you had the derivative, the second derivative of the position, which was the acceleration in F equals to ma. So you had the inertia in this case, namely the mass times acceleration. Acceleration is second derivative of position. Now you're dealing with the second derivative of charge, which is the equivalent of position, if you wish. The current was equivalent to the velocity. So there is a one-to-one correspondence. So mathematically, the two problems look identical between physics 4A and physics 4B. And as a matter of fact, this problem is so common in engineering and in physics that it has its own, basically, people in math, they deal with it. Actually, when you do a diffie-q, you're going to have this very same problem, and most likely, they're going to put one of the two examples, and most of the time, they come up with the RLC circuit. They say, remember what you did in physics 4B, or whatever you do in your E&M class, electricity and magnetism class? This is what we're going to study now in math, and they go in depth about it, okay? So let me share with you the screen to at least have a sense of what this problem look like. Where is the share button in here? Share. No, here. So I'm going to share my notes. And let me introduce the problem properly, okay? So what we're going to be doing now is RLC circuit. As the name suggests, you have a resistor, you have an inductor, and you have a capacitor, all three of them. This is basically like the ultimate thing that we have been dealing with so far. We first introduced capacitors, if you guys remember, in this order, and then we introduced the resistors after that, and then we introduced inductors. Of course, we had the batteries and all the things in between. So that was basically in a nutshell what we have in here. So imagine with me the following scenario. We have a battery of a given EMF, and the battery is connected to, we have a capacitor in here, C, and we have a resistor, R, and we have an inductor, L, and they're connected via what is known an AB switch. So you have an AB switch. So this is the position A, this is the position B of the switch. So what is an AB switch you're saying? It's a different kind of switch that it has this arm. Either it puts it in position A or in position B, one of the two, okay? So that is an AB switch. This is an AB switch. Not like a regular switch that you turn it on and off. This one can be in one position or the other position. Okay, it can be open like this one. There is nothing happening right now. Okay, so again, this is the EMF, this is a capacitor, this is RL. So this is what we're going to do in at t equal to 0. We're going to throw the switch in the position A. Okay, so in this case, this part of the circuit is disconnected. So the current will leave the capacitor, I mean the battery, and will build up charges in the capacitor. So at some point, there will be a charge Q0 sitting on the capacitor. Okay, and that charge, if you guys remember from charging the capacitor, will be simply C times, technically you need another resistor in here, otherwise this will charge immediately. Okay, technically you need a resistor in here. Okay, so technically there is another resistor in here. Okay, obviously this resistor, when we put the switch back in position B, will be disconnected of the circuit because it's only part of the first circuit. So there will be a charging cycle, in other words, that at some point we will have a charge sitting on the capacitor, and that charge is going to be C epsilon, and the voltage at that point, this is waiting for a long time. Basically, you have to wait for a long time. Remember, the charging from that section was given by C epsilon times 1 minus exponential of t divided by R, this R. So this, I'm going to call it the R1, if you wish. This is the resistor R1 times the capacitance. So if you wait for a long time, when t goes to infinity, at that point, the charge will be this value. And the voltage is always Q over C. So at that point, the voltage will be C epsilon over C, which is just epsilon. Okay, so that is basically the first stage. So imagine with me that we built a charge in a capacitor. So now, after that is done, so this is stage 1. At that point, we're going to throw the switch into position B and reset the clock. Namely, put t equal to 0 again. Okay, hit the reset button, and at that point, you have this circuit. You have a capacitor that has a charge, an initial charge Q0. You have a resistor, and you have an inductor. And it's connected together. So when did they get connected? They were connected at the initial time. Remember, I reset the clock. Okay, so this is a regular switch now. So this part in here at t equal to 0, the switch was closed. Okay, and the charge is equal to Q0, and the current is equal to 0. There was no current in this portion of the circuit. Okay. So if I apply Ohm's law in this case, starting from any point, it doesn't matter what that is. So we're going to see in here the current, doesn't matter, let's put it in here, the charge Q0. This is negative Q0. So in this case, the voltage drop, if I follow it from starting to finish, this is how it's going to look like. So there is a negative Ri in this point. Or we're counting the drops, so we're doing the drop. So it's going to be Ri plus the voltage drop in here is going to be LdI over dt, plus we're going to go from the negative to the positive, so it's actually minus Q over C is equal to 0. However, this is a discharge cycle, so it's Q and I are related to one another via this relationship with a minus sign in front of it. So let me clean this section here. So basically, I is equal to minus dq over dt. Okay. Having said that, I can replace it in here with the negative dq over dt, and this will be just simply di over dt will simply equal to minus the second derivative of q with respect to time. And this equation, when everything is subbed correctly, will give me L, the second derivative of Q with respect to time, plus R, the second derivative of Q with respect to time, plus Q over C is equal to 0. This is basically what Ohm's law will lead, what the Kirchhoff's rules will lead, okay? So this is the equation that we're supposed to be dealing with. If I did F equals to MA for the problem that I mentioned in the beginning, namely, we will find that M times the second derivative of X with respect to time, plus the coefficient of viscosity times velocity, and velocity is the derivative of X with respect to time, plus the spring constant times the displacement of the spring is equal to 0. It looks similar if I replace X with Q, and if I replace L, let's stick one side, the mechanics on one side. If I replace the mass with L, and if I replace the coefficient of viscosity with the resistance, and if I replace the spring constant with actually 1 over C. The mass is identical. So again, this is part of the argument for the analog circuits, okay? The math is the same. It doesn't matter which one you write. Both of them are the same, okay? As a matter of fact, we can abstract it and basically come up with any problem like this one. So this is a typical problem, what we are going to call, because there is an oscillator in here. This is a harmonic oscillator, as a matter of fact. Without the B, it's a harmonic oscillator, okay? But the coefficient of B in here introduces damping. So this is harmonic oscillations with damping. So this is a damped harmonic oscillator. Furthermore, because the other side is equal to 0, this is enforced. This is the full-fledged expression for it. Because there could be a forced damped harmonic oscillator, there could be a forced harmonic oscillator. Furthermore, you could have more than one oscillator. You could have coupled harmonic oscillator, 2 of them, or a multi-basically harmonic oscillator. If you take anything in here that oscillates, like molecules, for example, it could have all kinds of situations in here. So this is actually a typical problem that exists in a lot of areas of science, not just physics, engineering, and chemistry, and a lot of problems, solid state physics, a lot of problems basically can be reduced to this one. You build in a building, for example, and let's neglect everything but just the main parameters of the building, it could sway and swing one way or the other, and there's stresses under wind, for example, or earthquake. So you could approximate the entire building to a harmonic oscillator. The coefficients of damping in here, all kinds of frictions that are involved, and you have to keep the building from oscillating violently. So again, in this case, you have a harmonic oscillator, except in this case, it's a forced harmonic oscillator of the building because of the wind or the earthquake. So we'd want to find the response in that situation. Before we get into that, we need to find the solution for this one first. We need to understand this problem first, okay? Typical procedure in here, it doesn't matter which one you're looking at, physics 4B or physics 4A, okay? We usually, what we do at this stage, we divide by L in the first case or divide by M in the second case. It's the same thing. So we're going to divide by L in our situation. So once we divide by L, we will have the second derivative of Q with respect to time, plus, remember, I have an R over L now. So it's going to be R over L times dQ over dt. So this is the resistance part of it, plus 1 over LC times Q is equal to 0. Had we done the second one, it would have been the second derivative, which is the acceleration, plus B over M, which is just the basically the viscosity factor, plus K over M, which is just the omega naught squared. And this is the same thing, it's omega naught squared. As a matter of fact, I'm going to define omega naught in this situation in such a way it's 1 over LC. This is the natural frequency of the oscillator. R over L is a time characteristic also. R over L is actually tau. So I'm going to call tau now as just R over L. So the units for omega naught and tau are the same thing. Actually, both of them have the same units. So tau has the same units as omega naught itself. Not omega naught squared. Omega naught squared is 1 over second squared. I mean, yeah, it's 1 over second squared. whereas tau is 1/2. So this is something worth remembering, because if we're going to compare things, we better compare the apple to apple. And as a matter of fact, I'm going to divide it by 2 and define that as tau. So this is actually more appropriate to do the 2 in here in the denominator, and you will see clearly why that is. So the equation that is we're going to deal with actually looks like this. The second derivative of q with respect to time plus 2 tau, remember tau is just with a factor of half, so I have to divide by 2, multiply by 2, times the derivative of q with respect to time, plus now omega naught squared q is equal to 0. This is the same thing in physics 4b, by the way. Physics 4a, you would do the same thing. B over 2m will be called tau, and k over m will be omega naught squared, and the math will be identically similar to this one. If you're doing a diffie class, what you do in that case, you say, you know what, well, this is what I'm interested in. I'm interested in a solution of the type exponential of alpha times t, okay? I'm going to try this solution. And if you do that, the first derivative of q with respect to t will simply be equal to alpha. Of course, there's a coefficient in here that you need and all of that, but for right now, you're just trying to find what kind of an alpha that makes this exponential solution. That's all. So the first derivative will be an exponential times alpha t, and that is actually alpha times q of t, okay? And then you take the second derivative, which will give you the derivative of alpha is constant. That's the whole point of it here. So the whole point in here is just find alpha that makes this possible. So you take the second derivative, it's going to be an alpha squared times the exponential, and exponential is still q sub t. So you sub in the equation, and now you have an alpha squared plus 2 tau times alpha plus omega naught times both of them q, because the second derivative will bring a q, and the first derivative will bring q. So basically, you end up with this equation that looks like this: alpha squared plus 2 tau alpha plus omega naught squared. The whole thing is multiplying q sub t is equal to 0. Obviously, you would want a non-trivial solution. You would want q sub t not to be equal to 0, okay? So in this case, this equation must be equal to 0. So if this equation has to be equal to 0, then you have this quadratic equation that you need to solve. Remember, omega naught and tau are given. They're known already, okay? So they're actually, omega naught is 1 over square root of LC, and tau is R over 2L, I should say, okay? So having said that, now we can find 2 alphas, actually, not just one. So we said, okay, let's see if there is an alpha that does that. Here is the 2 alphas. First of all, and that's the advantage of putting the 2 there, because then this is basically, you can find using the quadratic formula in here for finding the roots of this quadratic equation. So it's going to be negative tau plus or minus the square root of tau squared minus omega naught squared. And that's it. That is the solutions that you have found. However, there are 3 possibilities in here. And a real problem. You could end up with tau equals to omega naught. And if that's the case, what you have actually, let's replace by its value, R over 2L must be 1 over square root of LC. In other words, R is equal to, what is it, 2 square root of L over C. If this is the condition, the square root in here is equal to 0. And there is only 2 solutions, basically, superimposed solutions tau, okay? Did I have the correct sign? I think I have a negative in here. I need the negative in here. It's important to have a negative in there. This is a quadratic formula. You have to have a negative in here, okay? So alpha is equal to negative tau, and this suggests the solution is somewhat equals to negative tau t. Because remember, I'm looking for q sub t that has this exponential in it, times something. This is not enough, because this is a differential equation of a second order, and it needs 2 constants. This will end up with just 1 constant. So if you really do this problem, you will have the solution has this general form, okay? I'm just giving you a hint of how the solution is. It's still dominated by this exponential. So the solution behaves dominated by this exponent, negative tau t, AB plus A plus BT. So this will kill the Q. In other words, Q sub t will go to 0 after a long, long time, because the exponential, the polynomial in here doesn't really dominate. It only has significance, but then the exponential after a long time t will dominate. So it's going to kill the solution. So in this case, we are calling this situation actually critical damping. Why is it critical? Because it's this condition. I assume that this denominator, radical in the square root in here is 0. So this is possibility 1. Possibility 2. 2. Tau is bigger than omega naught. So we said that tau is equal to omega naught, this is equal to 0. And if tau is bigger than omega naught, then I have really two solutions. Here they are. Alpha 1, by the way, this has importance when it comes to your lab, okay? So I'm going to call alpha plus is equal to minus, oh, we used lambda there, it's fine, minus tau plus the square root of tau squared minus omega naught squared. And I have another solution, tau minus is equal to minus tau minus the square root of tau squared minus omega naught squared. Both of these values are real. This is a real value, and this is a real value. Because tau, I'm assuming that the tau is much bigger than omega naught, or bigger than omega naught, doesn't have to be much. Then in this case, both of them are actually negative also. Not just real, but negative. This is clearly negative, because you have minus minus. This is also is negative, because you have tau on one side, and you have square root of tau squared minus something. So if tau, for example, is 10, and this is negative 10, obviously, plus 100 minus something. It doesn't matter what that thing is. Let's say, for example, 5, okay, or 1, as long as omega naught is not 0. Then what you end up with is square root of something less than 100, which is going to be less than 10. So you'll have a negative 10 plus something less than 10. Obviously, this is going to be, first of all, a negative number. It's definitely plus something. But that thing is less than this number. So it's going to be less than 0. So both of them are actually real, and both of them are negative. So the solution then in this case for Q sub t will be some constant times exponential of negative alpha plus t, and this decays to 0 also. Why decays to 0? Because this is positive. I mean, this plus plus. Let me write it completely, okay? Explicitly. It's much better to write it explicitly. So minus tau minus the square root of tau squared minus omega naught squared. I wrote it this way because I know this is going to be positive now. If this is 10 minus something, something is going to be positive, but the negative in here will make it that it's 0. So this is going to go to 0 no matter what, because alpha plus is negative. Plus b times the other one, which is definitely negative, tau plus the square root of tau squared minus, omega naught squared times t. So this is also is 0. Both of them will go 0 after a long time. So both of the solutions will go 0, and they'll go actually much faster than this one. So this is actually a case of an overly damped oscillator. This is overly damped. So what's going on in this situation is the resistance is winning, because I'm saying tau is much bigger than omega naught, and in tau there is R over L. There is R over 2L. And omega naught, there is no R in it. So the resistance now is dominating the circuit. So this means the resistor will kill the current right away. So the current that is established in here, trying to discharge this capacitor, will kill it immediately. In the first case, it was barely killing it, but it's going to go through and it's going to make it, but it's going to die also. Both situations, there is damping. Let's see the third scenario now, when actually tau is less than omega naught. So we examined two cases so far. We said tau equals to omega naught. This is the case of critical damping. Tau is bigger than omega naught. This is a resistance winning, basically, killing all currents in the circuit. So in this case, it's an overly damped circuit. That means that the resistance will kill and dissipate all the energy that was in the capacitor. Q naught squared over 2C is gone. It's gone in the form of heat. That's what this thing is saying, okay? Let's see the third case. The third case is when tau is actually less than omega naught. That means that tau squared is less than omega naught squared, which means that this number is actually a negative number, and the square root of negative number is actually an imaginary number. So the solutions are a little bit kind of strange in a sense. So this is how the solution would look like. So there is always an alpha plus, which is minus tau plus. Now I'm going to rearrange the expression here because I know now tau squared is less than omega naught squared. So this is more than that one. So I'm going to rearrange this expression and write it correctly. So I'm going to write it minus omega naught squared minus tau squared. Now this is positive now, but the minus, square root of a minus is a complex number. So this is going to be minus tau plus I, the square root of omega naught squared minus tau squared. Now all is well under the square root now, it's positive because omega naught is assumed to be more than tau. But there is this imaginary number that we need to handle because I assumed that I'm hunting for a solution of this type. And all of a sudden, alpha now became a complex number. So we need to make a real part of it. Otherwise, it doesn't make sense. There is no such a thing as a complex number in real physics. I mean, in real life, I should say. In physics, there is. Actually, quantum mechanics, if you look at the basic equation for it that is similar to F equals to ma, which is Schrodinger's equation, the first term in it is I. Is a complex number, a square root of -1. And it is the most precise science there is, quantum mechanics. And it is the basis of chemistry, the basis of everything. So, hey, complex numbers are here, okay? And they exist. But the solution at the end of the day, the atom is a real atom. The probability of finding an electron somewhere is a real thing. The energy level is a real thing. You can measure them as a spectral analysis of the atom for transitions between different energy levels are real. So any measurements you do better not have I in them, okay? The same thing in here. We ended up with an I somewhere in a solution, and that I better disappear, okay? Why? Because we said we're looking for a solution for this one. So we said, let's try it. And that gave us an I in the solution. So we better get rid of it when it comes to measurements, when it comes to actual things, because this is a real charge in the capacitor. The current that derives from it is real current that is going to go through an ammeter, and that ammeter will give you a real reading for the current. So at the end of the day, this I better disappear. And there is a way for it to go away, and we'll see that. But for a moment, let's hold on to it. There is actually a similar alpha also, which is going to be negative tau minus the same stuff in here, omega naught squared minus tau squared. So this 2 is the other one with the negative sign. And again, we have that annoying thing in here. So let's look at the solution now and see what it means, okay? First of all, we have Q sub t again is going to have this form. We will have a, which is just a general constant, and this better be complex now. This is, now we're dealing with complex stuff. Exponential negative tau t, and time is an exponential of this thing times t, which is the square root of omega naught squared minus tau squared times t, okay, times I, okay, plus another b, which is a constant also, times the exponential of negative tau t times this exponential of negative I, the square root of omega naught squared tau squared t. Because this is a real problem, what I'm going to require in here is that only the real part of this thing makes sense. So we're going to take an RE in front of it. So ignore the imaginary part because it's not going to be measured, that's all, okay? Because this equation is linear in Q. There is only Q to the power 1. Because of that, I can combine it with a complex conjugate, introduce a non-real part to the charge, and add them up. So in other words, I have a real Q and I introduce an imaginary Q, not a real Q, and add them up. The equation still holds for the complex charge. And then at the end of the day, remember to remove the imaginary part because it's just a mathematical trick at this point because of the fact that the equation is linear, which allowed me to do that, okay? So in a sense, I'm expanding this problem from the real plane to the complex plane. And at the end, if I'm going to put an ammeter in there or a voltmeter, I better remember to undo that. So that is the trick behind it. So at the end of the day, we're just taking the real part. Okay. So the real part in here, there is a formula. I don't know if you guys remember it from your math class or not. It's called the Euler formula. Exponential of I theta is equal to cosine theta plus I sine of theta. Did you guys do this in math or physics before? Yes, no? Does this sound familiar? Okay. When you do the Taylor series, okay? When you do the Taylor series, it's legitimate, okay? When you do the Taylor series in math, you did the Taylor series, guys, didn't you? In your math, yes or no? Okay, very good. So, okay, very good. So the expansion of the first of all, the cosine. The cosine function, cosine of x, if you do the Taylor series, is 1 minus x squared over 2 factorial plus x cubed over 3 factorial minus x to the power 5 over 5 factorial. Only the odd powers appear in the expression, okay? Plus x to the power 7 over 7 factorial, and so on and so forth, okay? So the next one is going to be actually a negative term, okay? But I'm going to put dot, 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 dot in here. You know what's happening in here, okay? The sine function is similar. Did I put the odd in here? It's supposed to be, oh, I'm sorry, I mixed up things, okay? Again, I blame it on me not having my copy, okay? So it's actually plus x to the power 4, I'm sorry. You guys need to catch up these things. It's x to the power 4. So the cosine actually is an even function. Because of that, it involves only the even powers of okay, good. I hope I didn't make another mistake, because usually I write the sine first. The sine is actually the one that involves the odd powers. I'm going to stop in here. Okay, so this is the expansion. And then if you guys remember, I don't know if you did the exponential, for sure you did. These are simple functions you must have done. So the exponential is just simply 1 plus x over 1 factorial plus x squared over 2 factorial plus x3 over 3 factorial. Because the derivative of the exponential function are just the exponential. And the Taylor series has the nth derivative, derivative of the function evaluated at x equals to 0, okay? Divided by 1 over n factorial and times x to the power n. This is the nth term in it. Because the exponential its own derivative, so the derivative of the exponential doesn't matter. Do it a million times, it's going to stay the exponential. Evaluated at x equals to 0 is going to be 1. That's why there is not term in here. And the n factorial coming from the expression of the Taylor series. So at the end, plus x to the power 4 over 4 factorial plus x to the power 5 over 5 factorial plus x to the power 6 over 6 factorial plus x to the power 7 over 7 factorial. And I need just one more term and we're done with this expansion thing in here. Plus stuff like that. Okay, here is the trick. You guys see the similarity between the exponential and the sine and the cosine? I mean, there is some, first of all, there's a plus everywhere in here. And this guy is alternating signs. So we're going to take that to our advantage. So we're going to do an exponential of ix and see how that is going to be. By the way, this is true no matter what you put in here. So if you decide to put, for example, Norco in the exponential Norco is going to be 1 plus Norco over 1 factorial plus Norco squared over 2 factorial. So whatever you put on top. So the fact that I put an ix in here should be the same thing. So here is how it's going to look like. The first term is 1 plus I times x over 1 factorial. And I'm going to take advantage of the fact that I squared is -1 and I cubed is actually equal to -I, and I is the first term to the power 1 is equal to 1, I itself, and I to the power 4 is equal to I, and to equal to -1, because -1 times -1 is going to be +1, and then I to the power 5 is going to be I to the power 4 times I, which is I to the power 6 is going to be I squared times I to the power 4, which is going to be, or I times I times I times I. Remember, every 2I squared is going to be -1. So this is I to the power 6 is going to be -1, and so on and so forth. In other words, it repeats with this periodicity, actually. Okay, I1, so this is the rate with which, so the first term is going to be this one for sure. The next term is going to involve an I squared, and I squared is a -1. So it's going to be -x squared over 2 factorial. The third term will have an I cubed in it, and an I cubed in it is actually -I times x cubed over 3 factorial. The next term is going to be I to the power 4, and I to the power 4 is a +1, x to the power 4 over 4 factorial. And if you do this, well, the next term is going to be I to the power 5, and I to the power 5 is an I times I to the power 4, which is just an I, plus I times x to the power 5 over 5 factorial. Since I did all of this term, let's finish them. So the next term is going to be -x to the power 6 over 6 factorial, because I to the power 6 is an I to the square times I to the power 4, and I to the power 4 is +1, and I squared is -1, so it's a negative. I to the power 7 is an I to the power 6, which is -1 times I, and that is going to be -I times x to the power 7 over 7 factorial, plus the last term in here is I to the power 8, and I to the power 8 is an I to the power 4 times I to the power 4, and both of them are 1. So it's going to be just x to the power 8 over 8 factorial, plus this thing is never ending. Of course, this is Taylor series. Look at the terms now that don't have an I in them. That's 1 minus x squared plus x to the power 4 factorial minus x to the power 6 factorial plus x to the power 8 factorial. That is actually the cosine with its signs too, alternating. So 1 minus x squared over 2, here is your x squared over 2 factorial, plus x to the power 4 over 4 factorial, here it is, minus x to the power 6 over 6 factorial, here it is, plus x to the power 8 over 8 factorial. Okay, so we have that. So the first part is actually a cosine. Now I have an I in front in here, and I have an I in front in here, and I have an I in front in here, and I have an I in front of all the odd powers. But then I have an x over 1 factorial, and here is your x over 1 factorial. Actually, I could write this one as because 1 factorial is just 1. Okay, x over 1 factorial. I have x to the power 3 over 3 factorial with a negative sign, exactly what the doctor ordered. And then I have also x to the power 5 over 5 factorial. Here it is, with an I out. And then you have a negative I out, and here is the other term. So it's I times the Taylor expansion of the sign, which is true all the time too. So this is true no matter what you have in here. So this is when Mr. Euler proved this identity. Now it's called Euler's identity or Euler's expression, okay? Makes sense? This is a mathematical proof for it. This is how actually he proved it. Okay, very good. So if you don't know this expression, this is a very handy and useful expression that we use a lot in engineering and use a lot in physics. So I'm sorry that you guys didn't see it in math, because you should have seen it the minute you did. You guys did the Taylor's expansion for the cosine, sine, and the exponential, didn't you?
Yeah, I did all of them individually, but didn't do Euler's identity specifically.
Okay. But you can take advantage of this. Look at this expression, how beautiful it is. Actually, look it up on YouTube. You will find a lot of people who are fascinated with this. Put x equals to pi. Okay. So what you have in here, you have sine of pi, which is 0. Okay. And now you have an exponential of I pi is equal to cosine of pi, which is -1. What do you expect more than this expression in the world? This is the most famous expression in the universe. Imagine all the numbers that you can think of coming together. 0, 1, the binary system, pi, the Greek letter that is a irrational number that fascinates everyone. E is also an irrational number, and I is the imaginary number. What else would you want in the world? This is actually one of the most famous expressions. This is coming from this expression, by the way. Okay, I know we're sidetracked a little bit, but this is for fun. Okay, so let's go back into the topic in here. So again, my point in here is we ended up with a complex numbers, which has this exponential in it, but the exponential is just cosines and sines, that's all, based on this expression. And they're cosine of this stuff, okay? So in general, what I'm going to say to the solution is the following then. Is Q sub t then, the real one, okay? So this is the real stuff, is going to be simply equal to some constant now. It has to be real now because we took the real part of everything. So this a may not be the same a as before. Remember when we do the integrations, we sometimes call a constant, and then the exponential of a constant is a constant. The real part of constant is ignore the imaginary part of it and just call it that constants, and so on and so forth. So there is a constant times the exponential of negative. Did I put the correct stuff in here? Yeah, I think I gave you the wrong units for yeah, they're correct. Everything is correct. I thought for a second that I gave you the wrong units for tau and so the tau has the correct units of -1 over a second, because it needs to cancel this second because at the end of the day, the argument of the exponential better be non-dimensional times a cosine of this square root of omega naught, because remember the I is gone when we do this expression. The I goes out. And when you take the real part, this whole thing is gone. So it's going to be a cosine of the square root of omega naught squared minus tau squared times t plus typically a phase. Plus a phase of some sort. So this is a phase shift. And this is a constant. Both of these are constants, by the way. That depend, both of these are constants, depend on initial conditions. Let's examine this solution because this is probably one of the most important case. This is case 3, by the way, that this exponential will kill it too, but there is oscillations in here. So this is a damped oscillations. This is really an oscillator that is damped. In other words, the charge will flip back and forth several times before it goes to 0, because this exponential will kill it at the end of the day. So this is damped oscillations. So in other words, the exponential will always kill things. And the last case, there are oscillations for the charge. It goes back, discharge completely, and then charges in the opposite direction for the capacitor. And then at that point, the inductor will push the current. And at the end of the day, it's going to do it backward in the opposite direction. So this one is actually will have more time to work with it. So let's plot all of them. First of all, let me write this expression in a more common, like the textbook writes it. So it's going to be Q sub t is equal to some constant exponential of negative. Remember, tau is just r over 2l. So it's going to be RT over 2l times the cosine of the square root of omega naught squared, which is just 1 over LC, minus r squared over 4l squared times t plus some phase. Okay, the phase and A and phi are determined by initial conditions. By the way, There were always two constants because this equation is actually of a second order. You will always have two constants. In the second case, you had actually two constants, and the two constants were A and B. So these were the two constants. Those two depend on the initial conditions. So initially there was a charge in the capacitor, or maybe there was a current also in the inductor. So at the end of the day, that's what dictates what A and B need to be. But at the end, the current and the charge will end up zero at the end of the day because of the presence of that resistor. Same thing in here. I needed two constants. So that's why the solution needed to be actually improved. And the two constants are A and B also. In other words, those two A and B will depend also on the initial condition. Although in that case, tau, namely R over 2L and 1 over LC had that condition on them, it's still true in that situation also that the current will die and the charge will end up to being zero at the end of the day. All three cases they do. So this is why it's a damped oscillator. So let me plot them a little bit to see how they look like. By the way, we could have done away with this exponential, okay? We could have done away with this complex numbers altogether if we made an assumption using trig only, okay? So this is not a necessary condition actually to solve these problems, to take them into a complex plane and bring them back, okay? But if we have done, it's going to be a little longer in terms of derivation, and that's typically what problems that don't involve complex numbers, okay? Here is the deal. First of all, by the way, I don't think that we're ready for the lab this afternoon. The lab has two portions in it. The one portion is easy, and I hope that you can do it quickly without even much help with it. And that is to build an RLC circuit. No, it's actually an RL circuit only, okay? And you vary you don't vary anything. You just turn on the EMF, turn on the battery, turn on everything, and start taking the time readings. So what you will see in this case is the voltage across the resistor starts from zero and starts to build up. Okay, I'm going to talk a little bit more about that part. But the point in here, the second part of the lab is actually deals with all of these things, number one. And number two actually deals with it in light of chapter 31, because I'm talking all of this problem with the second half equals to zero. All of this problem that looks daunting and complicated, and it is, I'm not saying it's not, the second half is actually equal to zero. What happens when the second half is not equal to zero? When there is actually a battery pushing a current in the circuit. Then in that situation, it will be this solution plus the forced solution. What if that source is actually not an AC, not a DC source, but rather an AC source? The problem becomes far more complicated. So at this point, I don't think that we're ready for this lab for this afternoon. So what I'm going to do is I'm going to post the instructions for you, hopefully by no later than Monday. And then we're going to meet a week from today, which is going to be the 19th. They're going to meet on the 19th for the lab, where we would have accumulated enough content to do both labs. Sounds good? Okay. So let's continue this. Let's summarize these things because it's quite a bit of things. Actually, if you look at the book, it's only one page, okay? And they don't get into a lot of math in there. So hopefully this will shine some light on it, okay? So here is the three cases. So I'm looking at the charge Q only, okay? As a function of time. If you follow the current I is simply negative dq over dt. So all you have to do is just take the derivative of everything that we're talking about. So the first case was the critical damping. And it looks no different than actually the over damping. So there is actually a linear increase a little bit, but then it's going to die out exponentially. So this is the case that I wrote that it's going to be A plus B times T times exponential of negative. In this case, it's going to be tau T. Okay. So in this case, the solution is going to die out. So this is the critical damping. In the case of the overall damping, it's going to immediately start going to zero. If you have shock absorbers on your car, on the suspension, you need this case. You don't want the next time your car hits a bump, your car starts to go up and down. Okay, that's not good. Okay, that is the time when you have to go and change your shock absorbers. So in this situation, you really want this scenario. You want to dampen immediately. And this is usually when you have a new car. So when you go and buy a car, used car, make sure to test it to see how good its suspension is, because it can be dangerous. So again, this is Q sub t, and this is t. So that in this case, is going to start immediately going to 0 exponential. They're much more rapid than this one. And the solution as Q sub t is equal to some constant times exponential of negative tau minus the square root of tau squared minus omega squared t, plus some constant exponential of negative tau plus the square root of tau squared minus omega squared, omega naught squared, that is, t, okay? That is actually another possibility for it. Where tau, if you guys remember, I define it as r over 2l. And omega naught is 1 over square root of LC. Okay, you need to remember those values. If we were doing mechanics, physics 4a, it's the same behavior, where r, this case in here, is going to be what? B over 2m, and this is going to be square root of k over m. Exactly the same thing. Okay? Mechanical system or an electrical system, it's the same thing. Now, in the last case, in this case in here that we examined, there is oscillations actually. So there is an envelope, which is an exponential function that is multiplying everything. So this is your exponential. So the dotted line is just the exponential of minus tau t by itself. But there is a cosine function in here. Man, I am not drawing it correctly. Can I get GeoGebra to help me with this in here? Or can you get this guy in here? Graphing. Let me stop sharing that screen and see if I can draw it better than this one in here, okay? I'm going to share with you this one in here. I'm going to go to the equations. I'm going to delete this equation in here. We're going to just write it as e to the power, open parentheses, negative. I'm going to take coefficient tau. I'm going to call it capital T. How is that? Times t times x. I'm sorry. Okay. Times cosine, in parentheses. We need to find the different square roots. So I'm going to call this whole thing as just omega. Okay. How are we going to call this one? I don't want to mess around too much with the. So I'm going to take omega naught to be 1 just to see how that's going to be. Square root of, open parentheses, of 1. No, let's make it a little bigger. Let's make it 4 minus t squared. Okay. And this one needs to be times x. And we're going to take the initial phase to be 0. How's that? Okay. So this is basically the graph that we want to graph and see if that's going to give me something in here. Okay. So we have a parameter t in here. So that we need to control the whole equation with it in here. So let's try to see how the graph look like. And because the value of omega, let's change the range in here. Let's change the range. What is the range? Plotting range. So we want to start from x equals to 0, definitely. That is basically what time starts from 0. And we probably want it to be just like, for example, 5 or something. And the value from x, let's start it from negative, let's say, for example, 30, that's fine, up to 30, just to give it symmetry in here. And let's say, okay. Obviously, this is too small in here. Let's blow it up in here, at least in the plotting range in here. Oops. let's make it into from -2 to +4, and let's keep this one positive. Okay, let's say okay. So this is how the graph looks like, but this is for t equals to 1. 4 minus, why it's not oscillating? Should be oscillating. It's being damped quickly in here. How about if I make this number smaller, 0.1? And let's see here. What? I don't see oscillations in here. Cosine of x times, what did I do wrong in here? Exponential. Let's make this one just -x, what's that? And let's make this one equals to 1. Let's plot this function now. I don't see oscillations in here, and there is a problem in here because x is, what's the problem in here? Oh man, I know what the problem is. Let's go back into the, change it to radius. Okay. So let's go back into the function. Graph. See now, all of a sudden we have a better behavior. Because the function was, the units I was using in the beginning were in degrees. So x going from 0 to 2 is just 2 degrees, which is hardly any kind of change in here. So for right now, you have plenty of variables to change. Okay, so let's go into the graph range in here again. Plotting range, and make this one 0, and make this one go all the way to 10 seconds, okay? And make the negative value in here from -2, for example, oops, -2, and to +2. That's it, okay? Because -1 is good enough. -1.2 is because of the fact that the cosine is actually less than 1, and the exponential at most is 1. So that's a good enough numbers. You see now the behavior. Makes sense now? Let me go back into my function and make it look nicer the way that I had it before. So I'm going to have a t times x in here. And I will have in here t squared. So I'll have that my parameter again, t squared. I'm glad that you saw that because you can clearly see again. So let's go back into the plotting range again. And let's make it from 0 again up to, let's say, for example, 10 seconds. And again, the plotting range in here, we know that this is going to be less than 1. So at most, I'm going to put it -1.1. And at most, I'm going to put it 1.1. And let's plot it in here. So again, t is 1. How about if t starts to increase now? This is basically the overly damped. This is exactly the critical damping. So I need to change the value of the range in here all the way to a much bigger value. Let's say, for example, to about 3. So if I put 3 now, the system is overly damped. If you don't see it, what's going on in here, it's immediately going to 0, okay? Oh, I'm sorry, because that is actually, I'm sorry, you cannot plot that because it's dealing with a complex number. 4 minus 9 is actually a negative number, so let's stick with 2, okay? And let's make this one 0.1 to simulate the case which is actually more practical, where you have actually a lot of oscillations in here. It looks like it's a lot of oscillations, and that is because of the fact that, let me go to the plotting range, we went just to 10 seconds. How about if we go to 100 seconds, okay? Does this make sense to you guys now? Very good. Let me plot the other function also. I know it exists. No, this is not responding. That's not good. Okay, so let me go into the other equation and write the other function, because there is another case in here where t is actually going to be more than 4. So that is, if you guys remember, has a solution which I'm going to simply, so let me write another y in here, equals to, I'm going to write exponential of open parentheses, negative in here, open parentheses, so it's going to be t plus the square root of, now remember t is more than the other one, so I'm going to write a t squared minus 4, because omega we're not changing it in here, and this, close that one, times x, close this parentheses, plus, so instead of doing that, let me just copy this whole thing in here, paste it, except in here it's a minus sign. Okay, so this is the negative solution, and let's enter this function. Let's make sure it looks good. So the first one has the alpha minus in it, and the second one is the alpha plus, actually, and both of them are in here. So this should be overly damped if t is actually correct in here. So let's plot this one in here, and let's go into t in here. The other one will go away, so let's make t equal to 3, and so we're going to look for the green line in here, because this program colors the functions in here correctly. So I'm going to go to values that are more, and let's go to a plotting range again, from 0 to, it doesn't matter in here, 10 seconds. And if we do this one, it's from negative 1.2 to some value in here. It's going to be more than 1, so it's going to be about 2.1. So this is how the graph would look like when t is actually more than 2 in this case, because remember omega naught squared is 4, so omega naught is, so if I change it now, the other one will appear, because now we are at the critical point in here. The blue one starts to appear, and that starts to oscillate, and as I said before, oscillate between those extreme values in here. And if I go back to the plotting range in here again, and the amplitude is less, of course, so it's 100, and this is the whole situation. Okay, makes sense? We spent on it far more than what the book has spent on it. I was thinking we're going to do problems. Actually, I have about 6 or 7 problems to do. But I'm hoping that you guys understand the physics behind it too, not just the, especially since you guys told me that you didn't do any of these things in physics 4A, or at least you don't remember having done that. Make sense? So here is the deal. You have a resistor, you have a capacitor, you have an inductor. They're connected in series together. In this situation, if the resistor wins big time, it's going to kill the current right away. So that's the behavior you saw when R, where T, I called it T in here because I wanted to call tau, and tau was proportional to R. So when tau was actually bigger than 4, in my example, the one that I was showing you, you saw that the system was damped, was going away right away, okay? In the critical situation also, it was damped too. Then, as a resistor became less and less, it started to oscillate and going to 0 still. It was going still to 0. So at the end of the day, all 3 cases are similar in a sense, because at the end of the day, the current, the charge will drop to 0 in the capacitor. So this is the case where T is very, very small. It's almost 0. So the resistance is very, very tiny. And as T starts to increase, as the resistance starts to increase, tau starts to increase, and the oscillatory behavior starts to disappear until at that some point, there is hardly any oscillation in here. It goes only one cycle. The charge completely reverses, but doesn't reverse to the negative value. It reverses to a smaller value because a lot of it was lost in heat. And then it's going to, this is the full cycle. From here to here is a full period, okay? So this is the first time when the charge has been reversed in the capacitor from Q to negative Q. And then it's going to go away, but by the time it starts to make the second cycle, it dies out. If R is less, then there is less dissipation in a resistor, so we'll have several cycles before it dies away. So it goes to the opposite, then now it's going through a second stage. So now the charge is positive on the same side now, so it's going to discharge again, and opposite, so discharging in here, there is no charge in here. At that point, the inductor is pushing current because it has energy, 1/2 of Li squared. So it's going to push it until now, all the charge is actually in the opposite direction in the capacitor. So in each time, the resistor is chewing away from the energy. Remember, the resistor has a power dissipation Ri squared. So no matter which direction the current is flowing, one way or the other, the resistor is wasting energy in the process. That's why you see this decay in here. So now we're in stage 2. Basically, we went through 5 full cycle. Now we are in this 3rd cycle, actually, a 4th cycle, and a 5th cycle, and a 6th cycle, and barely 7th cycle that you can see. And there is actually, if you look up close in here, you will see that this never goes away because the exponential never goes to 0, actually. So I'm going to zoom in into it, negative 0.5 or negative, let's make it negative 0.1 to positive 0.1 to see that indeed there are oscillations in here. This is 32 seconds in the process. And if you don't believe me, watch what happened after 32 seconds if I make the range even smaller. See, after 32 seconds, there is stuff going on. And if I want to make it even smaller, I don't know the precision of this calculator, how far it's going to go, but it's going to show me reading past this point in here. I don't know the divisions in here, 32 and 64. So this whole point is 32, so that's in 8. So this is 40 seconds now. So you see, past 40 seconds now, we are 48. So there is still oscillations going on. So it never really goes away completely to 0, but rather it's going to go to some to 0 at infinity. So it looks like way before 32 it's 0, but it is not. There is, if you look up close with tiny things, you're going to find it in there. Okay, here is the bad news. As daunting as this may sound, this is just the transient behavior of the circuit when you have actually a forcing agent in there. This is in preparation for chapter 31. 31 will have actually forcing agent on it. We'll have actually a battery in it. So what we're going to do then is we say, okay, remember the stuff we did in chapter 30? I mean, this discussion? That is just a transient. Ignore that, okay? Which is good in a sense. We're going to wait for the systems to settle down, and we're going to focus on the steady. You will discover that the steady is a little bit more fun to play with, okay? In other words, there is actually a theorem in calculus that says the following. In a non-homogeneous differential equation, it has 2 solutions, a transient solution, and that transient solution is a general solution, they call it there. And then they call the special solution, which is, they call it a special solution, but it's actually a steady state solution. So that is what we're going to be taking care of when we do chapter 31, because we're going to do an AC circuit. We're going to have a power supply. We're going to see what happened to RLC circuit, and we're going to get the resonance from it, okay? Because there will be driving force, and that driving force, the response in here could be minimal or could be dramatic, depending on what's going on in the circuit. And this is actually what the lab is, okay? So we have about 15 minutes. Can we do a problem? Yes, no, maybe? Yes? Come on, guys. How do you feel about it? Okay. I have one person at least who feels good about it. So let's do a problem. Okay, we have more people. Good, good. I'm proud of you guys. Okay. So let's see. I'm going to share with you the screen. You will see that it's usually much better to do problems than just to talk and talk and talk, or even with this simulation stuff. Okay. So I'm going to jump into chapter 30 problems, okay? So here are the problems that I'm hoping to do with you guys, okay? And if not, please do them on your own. Problems 38, problem 39, and problem 40. All of these problems are review for the exam, okay? Which is coming soon. And problem 44. 44 is actually a fun problem. Okay? But it's something that we need to do. Okay, more seriously, problem 58 and problem 52. So these are some of the problems we're going to be doing. So let's look at problem 38. Problem 38 says the following. For the circuit shown in figure 30.17, that is the figure I was showing in here, actually. This is a typical textbook example that we do in physics. This one, okay? C is 15 nanofarads, L is 22 millihenry, and R is 70 to 75 ohms. Calculate the oscillation frequency of the circuit once the capacitor has been charged and the switch has been connected to point A. So let me go back into the problems. So they gave us, so we're doing 38, by the way, okay? They gave us C, 15 nanofarads, or 15 times 10 to the negative 9 farads. They gave us also L to be 22 millihenry, or 22 times 10 to the negative 3 Henry, and R to be 75 ohms. Okay, and they want to find the frequency. Okay, the frequency, by the way, I probably didn't mention that, is just that square root of omega naught squared minus tau squared. Where is it? This is the frequency. It's this guy, omega naught squared minus tau squared. So that is omega. Square root of omega naught squared minus tau squared. This is the frequency with which it was oscillating in the graph that I showed you. Okay, so let's find that. Typically, in this case, myself, my preferred approach to these problems, in 5 omega naught, first of all. Omega naught is clearly equal to 1 over square root of LC. Okay, and that is 1 over the square root of L is 15 times 10 to the negative 9. L is 22 times 10 to the negative 3. It's clearly from here, 10 to the negative 9 and 10 to the negative 3, that's 10 to the negative 12. So if I write it correctly, it's going to have 1 over square root of 15 times 22, and then you have 10 to the negative 12 in the denominator. When you square root it, it's going to be 10 to the negative 6. When you take it up, it's going to be 10 to the power 6. Okay, so all I do in my calculator, instead of having to deal with those nonsense powers, I'm going to just do the square root of, open parentheses, 1 over, open parentheses, 15, I forgot to do 1 over, 15 times 22. Okay, and this is manageable, even with a small calculus. It says 0.055. So this is 0.0550 times 10 to the power 6. Obviously, I have 1, 2, 3. So it's 55 times 10 to the power 3 radians per second, or 5.5 times 50 times 10 to the power 4 radians per second. So this is omega naught. This is not omega, okay? I need to find tau. Tau is equal to R over 2L, and R is 75 ohms, and L is equal to 22 millihenry. And that is equal to 75 divided by, again, I could have pulled the 1000 in the numerator, but that's another thing, divided by 2 times 22 times 10 to the negative 3. I don't have to worry about the square root or anything like that because it's just the ratio of these two numbers. So it's telling me it's 1700 radians per second, or 1/2, okay? Remember, both of them have the units of 1/2. Now, omega is going to be square root of this omega naught squared minus tau squared. So now I have to take the square root of the difference of the squares. So it's going to be square root of, open parentheses, what is omega naught? It's this number. Oh man, I wrote it too many times. Oh, but don't forget that I need to square it, okay? So I have to square this number, because if I forgot to square it, it's not good. So I could have done it's 1/LC and all of that, minus this number squared. Squared. Okay, under the square root. Oh man, my calculator is not working correctly today. Square root of, open parentheses, minus. What's going on in here? Okay, let me do it differently now. Let's write it explicitly. Sorry about that. Okay, guys, you can do this, okay, can't you? Square root of, for some reason, square root of here is what you're supposed to do it, okay? I'm having difficulty with this calculator. It's not working for me correctly, okay? So I'm supposed, you guys are supposed to do this 1/LC minus R over 2L squared, okay? So you're supposed to do this one. So let me start it in here from scratch and see if this is, because it's giving me a red thing in here, the highlighted closing. I don't know what it's trying to say. And for some reason, it's not letting me write the argument of the square root. Okay, so it's 1/, okay, let me write it down again. Open parentheses in here. Let me go step by step in here. How are we doing on time? We still have time. We have 22 millihenry, 22, 10 to the negative 3. Okay, times 15 nanofarads, 15 times 10 to the negative 9. Okay, close the parentheses, minus, okay, we need R. R is equal to 75 ohms divided by open parentheses 2 times L is 22 millihenry, and millihenry is 10 to the negative 3. Close the parentheses, squared. No, actually, there is another parenthesis in here. I have to be careful with that. That's probably why it was complaining. And now close the whole parentheses. Okay, that's giving me 55,022.21. So it should really be 55,000 because we're supposed to keep only 3 sig figs. So this is a sig fig, radians per second. Okay. Hopefully, you guys, this is just, you know, that this is just a substitution. That's all. Calculate the oscillating. So this is what we mean by the oscillating frequency. It's not it's not the natural frequency. because it has been modified by this tau. Okay. So that's what the question that they are asking for, not 1 over square root of LC. Square root of LC is just the natural frequency without the resistor being in there. So that's going to shift the frequency slightly. Okay. How long will it take for the amplitude of the oscillation to decay by 10% of its original value? Remember, the exponential has, for the amplitude of the oscillations, the amplitude of the oscillation has an A exponential of negative tau t, okay? So this is the amplitude, that's the cosine. The cosine is not the amplitude, so this is the envelope. So this to go from this value at t equal to 0 to another value at t equal to 0 is just going to be A. And later on, the amplitude is going to be equivalent T1. We want the ratio of the new amplitude over the previous amplitude to be 10% of the original value. So in other words, the ratio of exponential of negative tau t prime times A over A, where the A cancels, doesn't matter what that is going to be 10% or 0.1. So if I take the natural log of both sides, I'm going to find the tau in here. So negative tau t1 is going to be the ln of 0.1, which gives me a solution for t1 equals to ln of 0.1 divided by negative tau. And tau, I found its value to be some value in here somewhere. Here is the value, 1700, okay? So if I divide ln by that number, remember ln of the fraction is actually negative. So ln of 0.1 divided by tau, and tau is 1700, okay? Oh, I'm sorry, there is a 2 in it. I forgot the 2 in here. There is a 2 in this. No, actually, that's good. That's part of the expression. It's a tau. So there is no 2 in there, okay? The 2 is already part of the part of it already. Part of the tau already. So the second, in seconds, it says 0.0135. So it's going to be 1.35 millisecond. That is how long it will take for it to go by 10%, okay? What value of R would it result in critical damping? So we need to change the value of R in such a way that tau is equal to omega naught. Tau, if you remember, is R over 2L, and this must be equal to 1 over square root of LC. So now I need to solve for R to make this possible, and that is going to be equal to 2 square root of L over C, okay? So that is the value of R that will make it into critical damping. And if I solve for that, R is going to be 2 times the square root of 22 times 10 to the negative 3 divided by 100 by 15 times 10 to the negative 9. And this will give me 2 times the square root of, open parentheses, 22 millihenry, 22 times 10 to the negative 3. I know. I'm saying, how about if you just do the powers? That's fine, we can. Divided by 15 times 10 to the negative 9, close the parentheses, close the other parentheses, and now get me what that square root is. And it's giving me 2,420 ohms. Or 2.42 kilo ohm. That is going to cause the damping to be critical. Okay, so this value is definitely less. 75 ohms is less. So it's oscillating, and it's oscillating with a big frequency, by the way. You can clearly see omega is huge, 5,500. And obviously, it's barely touched this value. This is omega naught. Omega naught, actually, initially, if I do the rounding, it's 5,000 or 55,048. And this one is 55,021. So it's barely less than omega naught, because R is very tiny. 75 ohms is very tiny. Whereas the actual R that makes this whole circuit go into critical damping is actually 2.42 kilo ohms, and you have only 75 ohms. Anyway, I hope this problem, we still have a few more problems to discuss from this chapter so that you guys learn this RLC circuit much more handier, okay? Again, the lab is going to be deferred to next week where we're going to go in detail about it for both labs. Make sense? Okay, very good. So I'll see you guys on Monday. Well, hopefully you already have the problems you're supposed to be thinking about. And when you come next time, these are the problems 39, 40, which are immediately next to one another, which means that you guys need to be watchful for this kind of problems in the exam. Problem 58 and 52, we're going to do them in the sequence, and then if we have time, we'll go back to problem 44 because it's kind of fun problem. It has to do with the solar activity. Okay. Okay, so I'll see you guys.
Sounds good. See you Monday.
See you Monday. So let me stop sharing. No, not sharing. Let me stop recording. What is that?